Now, the last part, and by no means the least important, though the story gets a little bit more interesting, is the Poisson distribution. Poisson distribution takes one parameter. It's called lambda. And this lambda can be anything that's from positive, anything non-zero, anything greater than 0 to infinity. But most interesting numbers will be from something non-zero to, 2, 3, 5, 10, 15, but not much larger. So this lambda, first of all, is called the mean arrival rate, the average arrival rate. Okay, let me say again. The lambda here is the average arrival rate. Why is it arrival? So what story, what picture should we think of when we apply Poisson distribution? Yeah, so this is the question. And before we get further into it, let's talk about why we have the word arrival. The scenario is a little bit similar to the story of having a shop and the customers arrive at the shop. Perhaps you have opened a lemonade shop or something. So maybe I can just quickly draw a shop. So your shop is here. All right. Imagine that you have a CCTV camera. So your camera records, although it's at a fixed point, it records people walking towards your shop, right? And then you unroll it digitally or otherwise. You unroll it and you start to see, people walking towards your shop. And just give me a little bit of your patience, please, because I want to do this in a way that is illustrative and hopefully accurate. Okay, so something like this. So what are we trying to do here? The people will, this may stretch across 1 hour, 2 hours, 5 hours. But just to make the long story short, let's say each interval is 1 minute. Yeah. So this is time. The horizontal axis is time. And when we kind of unroll that film, the digital film, we see people walking towards your shop to try to buy a lemonade. As they approach, we can put a time axis there, right? So here, every gap is 1 minute. I may not have drawn them entirely equally, but you get the point. Every gap is 1 minute. So then still, where is Poisson distribution? Now the Poisson distribution starts to come in when you count the number of people per minute. It need not be per minute, it can be 5 minutes or 10 minutes, right? So then you divide up. But you count the number of people per time interval. So here we will record 2. We'll record a 1 here, a 0 here, because we see nobody there. So there will be no fractional person. It's either in or out, all right? And there'll be 3 here, 0 here, 1, 1, 0, 2, 1, 0. You follow? Okay, now these are having the units customers per minute. Agree? Because we did count and then the gaps are on 1 minute interval basis. Then where is Poisson distribution? So first of all, the customers must be all independently arriving at the shop. So they cannot collude. They cannot call each other, hey, do you want to buy lemonade from that particular shop? Let's go together. So there'll be one whole group, right? So that will not follow Poisson distribution. So suppose every individual spontaneously, randomly, without discussing, without colluding with anybody else, just decided, I think I need to have a lemonade right now. I think I will go to this shop. And so he or she will be on the way to be captured by your camera. So if that is true, then these numbers will, when you plot a histogram, will form a Poisson distribution. Yeah, so to get to my desirable Poisson distribution, perhaps I need a tool here. Sorry, I'm kind of editing the facts, but facts are what I've created, right? So if you plot a distribution like this, we will transform this into a histogram, where our histogram will show, yeah, that this is 0, 1, 2, 3. So this, remember, X is the number of customers per minute. So if we are measuring the number of customers per minute arriving at our shop, and hence the word arrival rate. Yeah, arrival rate. So we say, how many times did we see a 0? 3 times. Yeah. How many times did we see a 1? 4 times. How many times did we see a 2? 1, 2, 3. 3 times. How about 3? 1 time. How about 4? 0 times. 5, 0 times, and so on. So then you start to see the formation of a Poisson distribution, which is going to look like this. So Poisson distribution is a discrete distribution, and the valid x values are all integers, starting from 0 and ending at infinity. And this is basically our Poisson distribution. So the lambda we need to calculate, because these numbers are what I have randomly generated, but it's probably around 0 point something, below 1, but I'll just follow my slides example, 1.5. Yeah, so in other words, if we do a 0 times the relative frequency of it, 1 times this, 2 times this, 3 times this, and so on, then it will follow Poisson distribution. Now, I have arbitrarily drawn rendered these numbers randomly, so I'm hoping that it forms a Poisson distribution. In real life, if you recorded these numbers, they are likely not exactly following Poisson distribution, right? They are going to be near to perfect Poisson distribution. So perfect Poisson distributions might be something like this. And it doesn't quite touch 0 until infinity. So the perfect Poisson distribution is always a little bit higher, a little bit lower, yeah, and never quite agree with any real life observed customer arrival rate histogram at all. Safe to say that, because Poisson distribution, after all, is a very arbitrarily constructed mathematical function. So there's no reason why any real life arrival customers will purposely form themselves into perfect mathematical alignment. Yeah. So then you will have to consult. Hey, wait, I think you're too fast. Let me slow down. I think you're too slow. Can you hasten up? It will become consultative. It will break the independence assumption. So real life observed data won't follow Poisson exactly. But remember the attractiveness of standard distribution like Poisson distribution. It is so close, right? So close that we are often quite tolerant of these slight deviations from the perfect Poisson distribution. So more correctly, I should say right? More correctly, I should say the green color represents perfect Poisson distribution. Yeah, so therefore you can see that if that is the case, and that the errors are always there, but the errors are always small also, then we are quite comfortable with just, why don't we forget about collecting 1,000 minutes of worth of data just to plot something that Poisson already is quite good, quite close at describing. You follow what I mean? So that's why it gives us an immediate quick bootstrap of our knowledge about our customers. And I use the word customer even on my slide here, because there are a lot of applications where we analyze customer behaviors, where we say customers, we don't know, right? We don't know customers when are they coming, and how fast are they coming, how rapidly are they coming. So this situation arises in many, many business situations. That's why it is a very important distribution to talk about in queuing theory, in business operations, in supply chain management, where customer in the broad definition can be ships arriving at a port, because that's one whole ship, many, many people inside, but that's one customer, right? It can be packets arriving at your computer after traveling through networks, where the packet is a customer. So it is invisible, but it is nevertheless very real. We even talk about digital assets now as if they can be weighted with a weight. So is that what is the story? A sort of a classic standard story to associate with this class of distributions. Yeah. So this is my story for you, so that you can then always associate with the most powerful, most representative story backdrop with this class of distributions. So a quick summary again. Let me take this screen away. Bernoulli distribution, the story is coin throwing. Uniform distribution, the story is a dice, six-sided dice. Binomial distribution, we're throwing 10 coins and counting the number of successes. Poisson distribution, well, you're selling lemonade and the customers arrive at a particular, random rates, apparently random rates. But when you gather those rates and ask, how many times have I seen 0 per minute? 3 times, right? How many times have I seen 1 per minute? 4 times. And keep doing that. When you plot the histogram of those instantaneous rates, Poisson distribution tends to appear. And that is the reason why we really want to make sure we understand this distribution.